Hi, thank you for taking the time for my session. It's titled BigQuery and TensorFlow. I'm Kaz. I'm a developer advocate, which is like an evangelist for developers. So I usually attend the events or meetups like this, talking about the Google's cloud technology or machine learning technology. I'm focusing on the data and the analytics products such as BigQuery, which is the data warehouse running on cloud, or TensorFlow, which is the open source machine learning library developed by Google. So today I'd like to discuss about these topics. Can I use this? So the main part is there are two parts. One is the BigQuery. I'd like to introduce what is BigQuery, how fast it can be, and why it can be fast. And the second part is machine learning, how you can combine the power of the machine learning with the data warehouse. And to combine those two technologies, I will use Cloud Data Lab, which is a web user interface for data scientists or data analysis, to combine these two technologies on web browser. So what is BigQuery? How many people have heard about BigQuery? Not so many, like 20 people? Like 10 to 20%. Thank you. So BigQuery is a fully managed petabyte scale enterprise data warehouse from Google Cloud. And this product is based on a very simple experiment we have done at Google Cloud many years ago. If you have a data on your disk drive, how many seconds you have to wait to read all the data? For example, if you have a 1 terabyte of data on your disk drive, how many hours you have to wait for copying 1 terabyte on disk drives to the other disk drives? If you have any experience on buying a new disk drives, nowadays those disk drives would have like 3 terabytes or 4 terabytes, and just backing up those data would take like many hours, 5 or 6 hours, or maybe one day. But what if you want to read 1 terabyte of data on disk drive in 1 second? Of course, you cannot do that with a single disk drive. You have to have multiple disk drives running in parallel. Then how many disk drives you have to run in parallel? The result of this experiment is that you have to have at least 5,000 or maybe 10,000 disk drives running in parallel so that you can read all data, 1 terabyte of data in 1 second. And we can do that because we have a bunch of the disk drives, tens of thousands of them on Google Cloud. It is called the data center as a computer. This is the biggest difference from our cloud and the other cloud. Because it's not just a data center building which hosts the bunch of the servers. It is designed to be working as a single computer with the tens of the thousands of the physical nodes. It's just like a massively parallel supercomputer. And one important technology is to build that data center as a computer is the container technology. As you may know, we have been providing many different consumer services like Google Search or Gmail or Google Maps or YouTube. And most of them are not running on virtual machines, VMs. We are not using VMs or virtual machines. Instead, we have been using our own proprietary container technology called Borg, B-O-R-G. So the Google services you are accessing, like Google Search, Gmail, or Google Maps, they are running on containers, that is running directly on physical servers. And there's no virtual machine layers. And the biggest difference from the popular container technologies like Docker and Borg is its scale. For example, a single Borg master controls 10 to 20,000 physical machines as a single cluster, whereas usually people are using like tens or hundreds of the containers for Docker containers. So at that scale, we have been doing the optimization of server resources such as a CPU resource or memory resource or I/O resources to have the best mix of those workload on CPU or I/O or memory. And any software engineer in Google can run a single Borg command to run his or her application or process on hundreds or thousands of machines, physical machines, in a few seconds. So that is the one important technology to build the data center as a computer. Another technology is Jupyter, which is a network fabric. We are not using the commodity commercial switches like routers or switches from the Juniper network or Cisco networks. Instead, we have been hiring many hardware designers, network designers, to build our own hardware switch from scratch. That is called Jupyter. That can host hundreds of thousands ports of the 10 gigabit Ethernet or 40 gigabit Ethernet. That can yield 1.2 petabit per second as a whole data center. That is super fast. It's just like a network they're using at the supercomputer. So by combining these technologies, you can build the massively power processing database or data warehouse. That is the basic idea of the BigQuery. Because we have the fastest network, we have the largest scale container technologies. For Google, it's not a big deal to build such a massively parallel processing query engine that runs your own single SQL with the hundreds of the servers simultaneously. So let me actually show the demonstration of BigQuery. And let's see how it can be so fast. So this is the tool called Cloud Data Lab. This is a web application running inside the web browser. And if you have any experience on data science or data analytics, you may have heard about the popular tool, Jupyter Notebook. Jupyter Notebook is being a de facto standard for the ad hoc data analytics for data scientists nowadays. And we have integrated Jupyter Notebooks to Google Cloud. So this is a pure Jupyter Notebook integrated with Google Cloud. So not only the Python code for data analytics, you can also write any other commands or SQLs to access Google Cloud resources. So in this example, I'm not using Python code. This is a SQL query running on BigQuery. So let's try this query. This is a sample query that is going to execute a query on a Wiki10b sample table. Wiki10b is a sample data which has the 10 billion rows of page views data, access log data imported from the Wikimedia service. 10 billion rows. And what I'm trying to do here is to find all the page view data for a title, Wikimedia page title, with the keyword cloud inside it by using the regular expression matching. And if you have any experience on actually using the database or data warehouse, usually you don't want to use the regular expression matching in the where clause or filters, because by using this kind of the pattern matchings, there's no way to build a database index for that query. So that means database or data warehouse have to read all the data from disk drive and do the text pattern matching and get the result. That is so-called full scan or table scan in database world. And any database administrator don't want you to run any full scan or table scan in the production environment. So they will be mad at you if you are really executing this kind of the pattern matchings on SQL. But with BigQuery, you can do that even with the 10 billion rows. Let me run it. Okay, now I have defined the SQL. And this is the Python code where I'm using the API of the Cloud Data Lab to execute the defined SQL from Python. So this is the result. As you have seen, this is the live demonstration, but still I got the result within like 10 seconds. Actually, it was like 7 seconds, I think. And this query actually read through all the I think it was about 400 gigabytes of data stored on the disk drives by full scan, table scan, not using any caches or indexes. And gathered, aggregated all the page view numbers for the Wikipedia access views, and got the real-time result. So it's a blazingly fast data warehouse. And this query was running on 1,000 to 2,000 CPU cores. And every single SQL query will be running on BigQuery will be processed by the 1,000 to 2,000 CPU cores. So that is the real massively parallel processing. And why the other cloud vendor cannot do this kind of the massively parallel processing? Because those other data centers are not designed as a data center as a computer. As I mentioned, the two technologies, the massively parallel container technology and superfast network technologies, were the enabler of this massively parallel query. So BigQuery is a fully managed no-ops data warehouse. You don't have to hire any database administrator for using BigQuery. All you have to do is put your application data directly from your applications, servers, front end, anything to BigQuery, and that's it. All the other things like optimization or maintenance, backing up, or the partitioning, sharding, everything is taken care of by the Google engineers. It can process the terabytes of data in tens of seconds. For example, if you are using Hadoop, Hive, or Spark, and if you are spending like tens of minutes with Hive query, those queries typically can be run in tens of seconds instead of tens of minutes. And BigQuery is super inexpensive. It's about 1/3 of the competitor's product. And it's so easy to access. As you can see, all you have to do is write down this standard query on web user interface, and that's it. So that was the quick introduction of the BigQuery. So what about using much smart analytics with the feature vectors? Let me actually show a demonstration first called Query Smart. This is a demonstration built on the BigQuery, which runs the SQL in a little bit smarter way. For example, you can run a document similarity search. With demonstration, you can choose one of these questions on Stack Overflow questions. So we have imported 10 million Stack Overflow questions and answer posts to BigQuery already. And by choosing one of those key questions, it will be this demo will be executing a query to find a similar questions to the specified questions. For example, if you're choosing questions about converting string to integer in Java language, now it is trying to find the similar questions from the 10 million questions imported on BigQuery. And this is not based on the index search or cached or keyword or label-based search. It is actually comparing the content between the key document, key question, and the 10 million questions imported on BigQuery. So as you can see, this is the left side is the key question, and this is the list of the similar questions, and the right side is the actual content of the selected questions. So as you can see, these are all similar questions posted on Stack Overflow. And I haven't used any labels or tags or caches or index to execute this query. This was executed as a full scanned, table scan query, comparing the content and similarity of the content. So how do you implement this? So these are the steps I have done with BigQuery to implement this query. At first, you have to do the segmentation of the sentences into rows. And then I have extracted the feature vectors for each post. That represents the content of each document or question. And then I have used the user-defined function, or UDF, to calculate the similarity between the feature vectors. I will explain what is UDF later. And then you can use the UDF in your own SQL to execute this similarity search on documents. So what is feature vector? If you have any experience on implementing your own similarity search on documents or content, maybe you may have heard about the technical word, feature vectors. Usually, if you are using the ordinary SQL, you may want to use the simple labels or tags like a music or content, movie or music or actor, on finding certain types of the content. It's easy, but if you want to a little bit smarter way of the query, executing query, maybe you can try using feature vector. For example, in this case, it defines the one vector with 3 numbers, and each number defines how much it is talking about a certain topic, like, for example, this content, as represented as a vector, talks a little bit about the movie and not so much about the music, but talks about so much about the actor. So this single vector can represent the characteristic or signature of your content. By content, I mean things like the document or images or audio or anything. And you can extract those feature vectors from the original Stack Overflow contents. In this case, you can find the words like Java or text selection or MD5. These are the very important keywords used in each document. So these keywords also have the frequency. So these are the vectors that represents the content of each Java Stack Overflow question. And by looking at the angles between 2 vectors, you can find the so-called cosine similarity, or simply it's a similarity between 2 vectors. For example, if you do the same thing with the words, then you can find the feature vector for word music has a very high similarity with the vectors for the words artist or drama or songs or dances. And you can do the same things on document or any other kind of content you want. And here you can use the user-defined function of BigQuery to implement this. Usually, if you want to implement this kind of the feature vector or search or feature vector cosine similarity search, you have to hire a bunch of the engineers who can build the Apache Hadoop MapReduce cluster or the Apache Spark cluster, writing a Java code or Scala code to build this kind of the sophisticated similarity search. But with BigQuery, you don't have to have any Hive or MapReduce or Spark cluster. All you have to do is write tens of JavaScript code to define a function that can be used in SQL, just like this. So by using UDF, you can define your own function to calculate the cosine similarity for the 2 parameters for 2 documents. It's so easy to calculate. And as I mentioned, every single SQL you will be running on BigQuery will be processed by 1,000 or 2,000 CPU cores. That means this particular JavaScript code would also be running on 1,000 or 2,000 CPU cores. That is one of the most large-scale distributed processing systems you can access on the cloud services. If you want to do the same thing with your Hadoop cluster, you have to wait at least a few minutes or maybe tens of minutes. But with BigQuery, your own JavaScript code would be running on 1,000 or 2,000 CPU cores in like 5 seconds or maybe 30 seconds. So let's take a look at the real demonstration, how you can build this kind of the content similarity search. All cells. So at first, let's take a look at what kind of data you have on the BigQuery table. which has the Stack Overflow questions. This is the original table. So it has the title and body of the questions. And the first thing you have to do is the segmentation. So now I'm running a query that has the user-defined function called segmentation. This UDF allows you to do the segmentation on the sentences and splitting the sentences into the rows by using the simple regular expression, like removing HTML tags or converting all the cases into lower cases. So you can easily get the result like this. Now you have the rows split from a single sentence. How to undo last commit in Git, blah, blah, blah. And you can do this kind of the sophisticated pre-processing by using the BigQuery only. You don't have to use any other clusters. And you can finish those data processing within 6 seconds. And after segmentations, you can do the extracting feature vectors by using TF-IDF algorithms. TF-IDF is a very standard or classic algorithm that allows you to extract the feature vectors from documents. This is not a machine learning. This is a very simple algorithm that counts the frequency of the words used in each document. And let's do that. And usually people have been using the Apache Hadoop MapReduce or Spark to do this kind of the TF-IDF processing. But with BigQuery, you can do that within SQL. And even if you're running the TF-IDF extraction against 10 million posts, it should finish within 50 seconds. Now we have the TF-IDF feature vectors. So now you can run your SQL by using these feature vectors, the similarity search. Here I have defined the user-defined function called calc similarity, which is actually a very simple the additions and multiplications between the numbers. And you can use the defined UDF to execute a SQL ordered by the similarity. So as you can see, the result is ordered by the similarity against the key document. It is all talking about adding or deleting columns in Microsoft SQL Server. So, as you have seen it, by using user-defined function on BigQuery, it's really easy to run sophisticated algorithms running on data warehouse. And now, this is the main topic of this session. By using BigQuery user-defined function, you can even run your machine learning algorithms or combine the machine learning, a result from the machine learning combined with the data warehouse. And why we need machine learning? Because by using machine learning, you can learn how to analyze data with much complex features. For example, if you have your own e-commerce site selling fashion items like T-shirts or skirt or anything, pants, anything, then you may want to extract the taste or the fashion trends are made by the consumers or human senses. And it is really hard for database engineers to capture those human senses or instincts by writing down the SQL, because there's no clear tags or labels or indexes that represents the very complex and fast-changing fashion trends or taste. Instead, you can use the machine learning, specifically neural networks, to extract how it looks like or what kind of the pattern it has. For example, a certain types of the consumers likes to buy a certain color or certain types of the fashion item. By using machine learning, you may be able to extract that kind of the patterns by using machine learning. So let me show the actual demonstration how neural network works. This is a very simplified demonstration, but by putting the training data from here, x1 and x2, and by training the machine learning algorithms by saying that these data are in the orange group, and these data are in the blue group, and there's a certain patterns, like a double spiral in this data set, so that gradually computer tries to find these complex patterns by tweaking the connections between the neurons inside neural network. So now you found that the neural network here is able to classify these complex double spiral patterns, just like humans do. So in this demonstration, I haven't done any programming, or I haven't defined any SQL query. Instead, what I have done is just keep providing the training data. These are the data points, and these are the human classification result by humans, like it should be orange, it should be blue. Then computer automatically can find the complex pattern from it. So this is the reason why we want to use the machine learning for your problem. And from Google Cloud, we provide two different kinds of the machine learning products. One is pre-trained machine learning models, and another is custom ML models. Pre-trained models provides the pre-trained machine learning model, so you don't have to train your own model. Instead, we provide the simple models for the vision object recognition, or your images, or speech recognition, or translation, or natural language understanding. But in this session, we'd like to focus on these custom ML models because we want to use machine learning to solve your own business problem. And for these purposes, we provide two products. One is TensorFlow, which is an open source tool for build your own neural network machine learning model. And machine learning engine, or ML engine, is a fully managed platform for running your TensorFlow model on Google Cloud. TensorFlow is the latest machine learning library we have developed at Google, and we have open sourced it in November 2015. And this is the real machine learning framework we are actually using inside Google for developing any new AI or machine learning products. And by using TensorFlow, you can write tens of Python code like this to define a neural network. And also, by using TensorFlow, you can let the TensorFlow to do the most important and the most hard part, the hardest part of implementing your neural network, which is the optimization. And if you have any experience of reading the textbook for neural networks, you may have saw the keywords like backpropagation or gradient descent algorithms. So you need to understand all the math formulas and how to implement those formulas by yourself. But by using TensorFlow, you don't have to fully understanding those complex math things. All you have to do is write a single line to call an optimizer of TensorFlow to solve the problem. And Cloud Machine Learning Engine, or ML engine, is a fully managed runtime for running your TensorFlow code on cloud. It provides the distributed training, and it can provide the access for the tens of CPUs and GPUs. And I'd like to show two use cases of the combination of machine learning engine and BigQuery. The first use case is here using BigQuery for pre-processing. It's the most popular use cases. Because in many cases, for using machine learning, you have to try out many different approaches for the pre-processing. For example, the cleansing of your data, or padding, or reformatting, or converting, normalization. You may want to try different ways of pre-processing. And BigQuery is the best tool for that. So let me show the actual demonstration where you can use the BigQuery for pre-processing. This is another simple demonstration called classifying Manhattan with BigQuery and TensorFlow. In this demo, I will be training a simple neural networks which can classify whether a point, geopoint, is in Manhattan or not. And to train the neural network model, I'll be using BigQuery to extract the training data from data warehouse. So this is the SQL query I'll be using for extracting the training data. I'll be using a sample table called NYPD collisions. This is a public data set imported from the NYPD database, which has all the records for the car accidents happened in New York City. So let's take a look at what kind of the data it has. So this is the training data we'll be using. It has all the car accident records happened in New York City with the borough, latitude, and longitude with timestamp. And we'll be using these pairs of latitude and longitude and borough data to train a neural network model. But if you take a look at the raw data, there's some rows that cannot be used for training data because some data is useless. It doesn't have any borough, or this row doesn't have any data, just timestamp. So we have to exclude those data. So to do that kind of pre-processing, like a cleansing or reformatting, or adding new flag, like is Manhattan or not, you can use the SQL or BigQuery, or you can even define a user-defined function to do that. So I have defined the SQL, and now I'm executing this SQL from Python code. And the result will be converted into a NumPy array. So now I'm getting the result. It's taking time. Yes. So now I got the 10,000 rows of the pairs of latitude and longitude with the flags whether each pair is in Manhattan or not. This will be used as a training data. So let's take a look at how does it look like. So this is the training data. It looks like the shape of Manhattan. And you can even find there's a Central Park here. So let's start training your model. So I have split data into training data and testing data. And this is where you are using the TensorFlow. So now TensorFlow has the so-called high-level API. So it's getting much easier to define your deep neural network. In this case, I have just written like 4 lines of code, like this, just calling GNN classifier to create your own deep neural network classifier with the hidden units with 4 layers, and each layer has 20 neurons or 20 nodes. So I have finished defining a neural network. And before start training these neural networks, let's take a look at how stupid it is. Before training the network, all the neural networks is randomly initialized, so it cannot work. It doesn't work. So just like this, it recognizes these blue parts are Manhattan. So we have to train this model by calling the fit method of the GNN classifier and passing the training data extracted from BigQuery. So let's do that. So I'll be executing 100 steps for training. And as you keep training the model, you'll be gradually the model getting much smarter and smarter. Try to capture the shape of Manhattan. So the result is not 100%. Usually the machine learning model cannot achieve 100% accuracy, but still it's pretty much higher accuracy, 99.4%. And if you keep training the model, you'll be getting much higher, like a 99.9% accuracy. So in this demonstration, you have seen that it's so easy to use both BigQuery and TensorFlow within the same environment, Cloud Data Lab. Let's take a look at the use case number 2, which is the combination of BigQuery and machine learning in opposite way. In this case, we'll be using machine learning engine, TensorFlow, for extracting feature vector so that we can run a much smarter query on BigQuery. So going back to the query to smart demonstration, this demonstration has another menu called image similarity search, where you can choose one of the key images to execute a similarity search against 1 million images. For example, if you choose this jellyfish, now BigQuery is running a similarity search against 1 million images. Again, this is not a query based on tag or label or index or cache. It is actually comparing the content, the images, its color and shapes, texture, patterns, and trying to find the similar images. Not looking for jellyfish, but it was looking for similar images. So that's the reason why sometimes you get things like this. This is a moon, but it looks similar. Same color and pattern or texture. And these are the steps I have done to implement these demonstrations. At first, you have to import all the 1 million images on Google Cloud Storage. And then I have run the CNN, or convolutional neural network, which is the most popular neural network model for analyzing the image data. And usually, people are using CNN for extracting labels, such as a jellyfish, or a flower, or mountain, or vehicle. But in this case, I've just thrown out all the labels. Instead, I have extracted feature vectors from those CNN. And then imported those feature vectors on BigQuery and used user-defined function to calculate the similarity between two feature vectors. So by using CNN, usually people are using labels at the final layer, but you can also extract the vectors from the final few layers of the CNN. And by using TensorFlow, it's so easy to do that kind of customization. And also, by using machine learning engine, you can use the tens of the GPUs for executing this batch processing in parallel on the cloud. So you don't have to buy and maintain your own GPU server. Instead, you can just rent a GPU servers, tens of GPU servers for a short time period, so that you can extract feature vectors for images. And by taking a look at the similarity or distance between two vectors, you can easily find similar images for certain images. And again, we can use the BigQuery user-defined function to calculate the similarity or distance. And once you have defined your user-defined function and imported the feature vectors for your content, you can use those feature vectors and UDF on any SQL query you want to use. So that means you can allow any other people, other than the data scientists or data analysts, like salespeople or your execs or marketing researchers, directly accessing BigQuery to run their own business queries by using the power of the machine learning. So let's summarize what we have looked at. So BigQuery is a fully managed large-scale, petabyte-scale data warehouse. It's blazingly fast because every single query will be running with the 1,000 or 2,000 CPU cores. But the most important feature of BigQuery is user-defined function, UDF, because that might possibly replace your Hadoop MapReduce cluster or Spark cluster. And by combining UDF with machine learning, you can implement much smarter query, like comparing the feature vectors and calculate the distance or cosine similarity with those vectors. So that, just like humans, your query can have a human sense or instinct to find the best products from your e-commerce site, or making recommendations, or finding spam users, premium users from gaming servers, anything. And I have shown the two examples, document search and image search. And these are the only few examples for all the possible applications of this technology. It can be applied to any content where you can define any feature vectors. For example, if you can define feature vectors for your user in your gaming service or consumer services or e-commerce service, then you can easily find the similar users, premium users or spamming users, cheating users, or the potential users. If you can define feature vectors on your products, you can easily build your recommendation systems on BigQuery. You can define feature vector on your sensor data from IoT devices. You may try using BigQuery for finding bad IoT devices that could cause their future failures. So if you are interested in these technologies, all the source code is now open source, so you can go to GitHub and search with the query smart. Thank you so much.
Actually, we have a lot of questions. I will try to cover all of them. So, does BigQuery currently, or will it, support user-defined aggregate functions?
Yeah, that's a good question. Unfortunately, at this time, it doesn't support any aggregation. So it applies to a single row.
Can you stream data in order to populate BigQuery table?
Can you feed what?
Stream data.
Stream data. Yes, BigQuery has the streaming API, so that, for example, the largest customer for BigQuery is streaming like less than 10 million rows per second by using the API.
Which database would you recommend for big data?
If it's for analytics, just like the demonstration I have done, then BigQuery is the best data warehouse. If it's a transactional data, the data you want to update, like the user status or user session data, then you may take a look at the Cloud Bigtable or Cloud Spanner. These two databases are the transactional or designed for the transactional use cases. Yeah.
Someone is interested in your opinion. What do you think about using strongly typed program languages like Java, C# for BigQuery? Can we do fast BigQuery with them?
Using Java or C# on BigQuery?
Yes.
Unfortunately, it is not supported at this time. Yes, it only supports JavaScript.
And how often is training set being updated?
How often what is updated?
Training set.
Training set.
Yes.
It depends on how you can build the systems. In this case, we have designed the systems as a batch processing systems. So anytime you want to update the feature vectors, you have to run the batch processing with the ML engine to extract the feature vectors from those images.
Any more questions in the audience? No? Thank you.
Thanks so much.
Sorry, we have one question. Yeah.
Sorry. The question is, as you know, as we all know, that 80% of data scientist work is all about data wrangling and data extracting and feature
Pre-processing, yeah.
Pre-processing. So you mentioned that approach with neural network for feature extracting. But as I know, there's still a gap between data structure for machine learning approaches. So it means we have a lot of data models for business intelligence, multidimensional, any other, graph databases and so on, but no structure for machine learning purposes. What are you thinking about that, and what direction to democratize data structure for machine learning to decrease this underwater work of data scientists?
It is true that BigQuery could not be a silver bullet, so BigQuery is not the only one solution. But if it's a really simple task like padding or cleansing or just a transformation of data, then, as I shown with demonstrations, you can write JavaScript code to use things like a regular expression matching or JavaScript syntax to very easy pre-processing against data. So I think that can cover majority, maybe over 50% of the use cases for pre-processing. But for the other cases where you may want to do more sophisticated analytics on the unstructured data, then we have other options such as the data proc, data PROC, data proc, and data flow, yeah. And data proc is provides the easy GUI to define how you want to pre-process your data. For example, if you have a certain date columns, like a user data, user birth date, it can provide the automated transformation of those user date formats. But if you really want to do the more serious conversions of your data or unstructured data, but you can use the data flow, which is just like the Apache Hadoop MapReduce or Spark, where you can write any Python code or Java code to write your arbitrary logics against data. But I think in general, this is my personal opinion, but the success of your data analytics or data science is totally depending on how fast you can run the iteration between the pre-processing and training and validation. And BigQuery is the best platform for that, I think. Because if you're using Spark for that kind of pre-processing, you have to wait for like minutes or tens of minutes. While with BigQuery, most of the query can finish within 5 seconds or 10 seconds or 30 seconds. So that the data scientists can try out many different ways of pre-processing. So I think that's very simple but powerful tool for data scientists. Okay, thank you.
Thank you.
Thank you.